Okay, so let's go ahead and start then with 8.3. Just take down, you can translate it. I'll get it on there today. Sorry about that. Okay, so first of all, what we're going to look at is a geometric series. We've talked a little bit about series, and the idea, let me just make a sequence, kind of give you an idea of a geometric sequence. It's actually very easy to make a sequence. What you do is you can start with a number, whatever, okay, and I'm just going to, you don't have to write this down, just pay attention to this. And then if you multiply by the same number over and over again, so let's say we multiply by 4. So 1 times 4 is 4. 4 times 4 is 16. 16 times 4 is 64. That would be a geometric sequence. And what R is, the letter R stands for that number that we're multiplying by over and over again, okay? Well, how do we make something into a series? What we do with a series is we take a sequence, but what we do is we add the terms. So you could take that geometric sequence and turn it into a series. And what happens with a series, an infinite series, is sometimes they converge, and there's sometimes we have the ability to find the value of that convergence. Most of the time, we're not going to find the value of the convergence, although we are on a geometric series. Here's one more example. Let's just start anywhere we want to. Let's say we have 3, and let's say we multiply by something like a half. Well, 3 times a half would be 3 halves. If you did 3 halves times a half, that would be 3/4. And then if you kept multiplying it by a half over and over again, you would have that. So that would be a sequence, a geometric sequence. And then the series would be, well, we just add them all up, okay? And sometimes it'll converge to some value, sometimes it will diverge, okay? So that's what we're looking at. So to start with some basic terminology, we've already looked at a geometric sequence. Typically, like in this sequence right here, R would be equal to 4, right there, because I'm multiplying by 4. And then this thing would be written like this. It would be written as 4 to the k power, like that. So if you think about this, this right here would just be 4 to the 0, right? This would be 4 to the first, 4 to the second, 4 to the third, and so forth. So you generally have this format right here. You have that ratio to a power, okay, like that. Does that make sense? Okay. And see, like with this one, it'd be the same thing. R would be equal to a half this time, okay? Then what you would have on this is you would have some sort of a form like this, where you would have 3 times 1/2 to the k power. And then 3 is going to be like that constant. So if you look at this sequence, that's always there, isn't it? Okay, that 3 is always there. And like this first term right here would just be 3 times 1/2 to the 0. This term right here would be 3 times 1/2 to the first, and so forth. So tell me if you understand that okay. Okay? So a geometric sequence is very simple. You have a starting point, and then you multiply by the same number and over again, and that value R is the ratio. So what we are going to write on here, you can just write these words if you want to. You don't have to write all this out. You can transfer this later. A geometric series is a series in which the ratio of successive terms in an underlying sequence is a constant. Okay, and that ratio is like what I showed you over here, like R is equal 4 there, R is equal to a half there, like that. Okay, thus a geometric sequence generally has the form, a geometric series. We usually use that sigma to represent a sum, and then it's going to be like AR to the N or AR to the K, like that. And R is going to be the ratio of the terms like that. Okay? So that's the idea. Is there any question about what I mean by a geometric sequence and what a geometric series is? What's a series? What's the difference between series and sequence? You're adding things up. Okay? That's the idea. All right? So the idea on this is, here's a good example of a geometric series right here. So basically A is always the first term. That's a good thing to write down. So in this particular problem, 3 is what A is, and R is what you're multiplying by each time. So what are you multiplying by to get the next term? by 2, right? Okay, you got like 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24. So it goes like that. That's the idea. You guys can also take pictures if you want to. I see you got your phone there. So that's fine. I don't care if you guys do that either if you want to. Okay, so the other thing that we would have on this is you can factor the 3 out of here. And if you were writing this, it would go like this. You could say on this, since it has this form, AR to the K, you would just say 3 is the first term, and then you would say the ratio is 2, and then like to the K power like that, okay? And then just kind of in your mind, make sure that that's right. I mean, if K is 0, what's 2 to the 0? 2 to the 0 is 1. 1 times 3 is 3, right? If K is 1, then you have 2 to the first is 2 times 3 is 6. You guys see how that works? Okay. So anytime you have that geometric series, then you can generally, if you can figure out A and R, then you can write out what that formula is. That's the way that works out. Okay? All right, so this is kind of how we do this. Now we're going to look at trying to develop a formula for the sum and kind of talk about the convergence of this then. Okay, so here's one more example. Like on this particular series right here, what's A in this particular series right here? 0.9, that's easy. It's always the first term, okay? What R is what you're multiplying by. So if you think about this, what you're multiplying by basically is you're ending up with, you're adding 1 decimal. So that's got to be a 1/10, okay? Or a 0.1 is what you have there, okay? So notice that that's A, and then that's R right there. And then we're going, if K is equal to 0, then K is 1, 2, and then K is 3 like that. So that would be a series of 4 terms, K going 0 to 3 like that. All right, does that make sense? Okay, what's A? That's important. First term. What's R? It's what you multiply by that constant to get the next term. Everybody solid with that? Okay, that's what we mean. Now, what we're going to do with this is we're going to develop a formula on this. So what I'm doing is I'm writing this term out like this. S of n is standing for the sum of that infinite series, okay? And then it can be like a partial sum. So the first term is A, then you're multiplying by R over and over and over again. So tell me if that makes sense. Your first term's A, right? Then what do you do to get the next term? You multiply by R. Then you multiply by R again, so you get R squared and so forth. Does that make sense? Okay, so that's the general formula we have. Now what we're going to try to do on this is we're going to try to develop a formula. So I'm going to take you through this idea. So what I'm going to do is we're going to take this formula right here, and we're going to multiply both sides by R. And we're going to do a little derivation on this because we're going to get a formula that's real important. So I'm going to do that. Then I'm also going to multiply the right side by R. So I'll have that like this, and then you just have the dots to represent the pattern that you're going through, like that, okay? And then what we're going to do is we're going to subtract the result from the original equation. So what I want you to do is let's write down the original equation. S of n is equal to A plus AR squared, and we'll go out all the way to the end to get AR n minus 1 like that, okay? All right, and the reason we're doing n minus 1 is because we're generally starting this at n at 0, okay? Then what I'm going to do is I'm going to write this second part underneath this. So let me highlight this and kind of show you what I'm doing. So I'm going to multiply that out, that R through everything, then I'm just going to basically subtract these terms. So I'm going to take that first term would be AR. So I'm going to subtract it. That second term is going to be minus AR squared. Okay, and then that third term, you're just going to keep going like this forever. Now check out what happens here. This is kind of important. If you do AR to the n minus 1 times R, can you tell me what you would get on that? AR to the n, right, good. Okay, because remember you're adding these exponents. So you have A r to the n minus 1 plus 1. You're going to add the exponents on that part right there, so you get ar to the n like this. So out here, you're going to end up having a minus ar to the n like that, okay? Now, let's think about what happens. You have to do this a lot of times when you're doing series. You see a lot of cancellation, right? That's going to cancel, that's going to cancel. How about that? That will cancel with the previous term to this. The term that's right before this now is going to end up being, you got ar to the n minus 1 like that. So that one is going to actually cancel. You're going to be left with this, and you're going to be left with this. Okay, what comes after n minus 1 anyway? You add 1 to n minus 1, what do you get? You get n. So see, that one's left over, but that one's going to cancel right there. So you want to show that cancels, even that cancels. So you're left with s of n equals a minus ar to the n, like that. Does that make sense, what I'm showing you? Okay? See, this one is the one that's going to be left over then. So what you have then, after that cancels, probably what I should have done is wrote this more like this. You might see this a little bit better. You'd have ar to the n minus 1, and then eventually you would have minus ar to the n. Okay, so everything cancels. So if you write what you're left with, you would have s of n equals a minus ar sub n like that. And then we're going to get that solved right like that. Okay, and then the other thing I forgot to do on this, which is pretty important, is I'm subtracting this. Okay, so see, I'm just subtracting that second expression from that, so I need to correct myself on this. Sorry about that. So this side right here is going to be Sn minus r times Sn, and then the right side's going to be a minus ar sub n like that. And then we're going to solve this equation for s of n. Okay, does that look reasonable, what I'm doing? That's something that you're not used to. You're not used to using infinite terms and doing something to both sides, but it's the same basic idea. Okay, so if we're going to solve for s of n, what would you do to the left side? What does it look like you can do algebraically to the left side? You can factor out an s of n. Good. So we have s of n times 1 minus r. Okay, now I'm going to leave this alone. You could also factor that a out if you wanted to. Then what I'm going to do is just divide both sides by 1 minus r, like that. So what I get is I get the result, s of n, and then I'm going to go ahead and factor the a out now. So I have a times 1 minus r to the n all over 1 minus r like that. And then that's the conclusion. So that would give the sum, that would give you a formula for the partial sum of a geometric series. Okay, like that. All right, so what that means is, like, if you wanted to find s of 3, well, that just means that you would go through and you would just use, a is the first term, r is the ratio, in this case n would be 3, and that would give you the sum. Okay, that's what that is. So that's a pretty important formula for what we do in this section. That's the derivation of that. Any questions about that? Okay, now we're going to, on the next page, what I want to do is I want to run through just kind of showing you how this works. So we're going to verify a couple of sums on this then. Okay, like this. So basically, let's verify this right here using this formula. Okay, this is a geometric sequence. So let's go ahead and work with 1 plus a half. Okay, I'm just going to verify that the formula that I just gave you, which is this right here, I'm just going to verify that it works. Okay, first of all, if you looked at this problem, let's figure out, first of all, if you added that together, you'd just have 2 halves plus a half. So that partial sum would be 3 halves. Okay, now let's use this formula right here and see if it works. Okay, tell me what a is in this sequence. This sequence or series only has 2 terms. So that's 1. Can you tell me what r is? 1 half, exactly, because you multiply 1 by a half to get a half, like that. Okay, now what is n in this problem? How many terms are there? There are 2. Okay, so we got 2 terms. Okay, so let's go to this formula right here, plug it in, and let's see if it works. Okay, so A is going to be 1. Okay, so I'm going to write this more like this. I'm going to write this as S of 2 is equal to A, which is 1, times 1 minus 1/2 to the second power. There's 2 terms, and then 1 minus 1/2. So if we work out the details on that, we should get 3/2. So let's just prove that to ourselves. Now n is going to be 2, so I need to plug that in like that. Okay, does that look good to everybody? A is the first term, R is what you multiply by. That's the common ratio. Okay, work it out. It looks like you're going to have, in the numerator, you're going to have 1 minus 1/4. 1/2 squared is 1/4. 1 minus 1/2 is 1/2, like this. And then if you got a common denominator, you could change this if you wanted to 4/4 minus 1/4 all over 1/2. So that would be 3/4 over 1/2. And if you work that out, that's a division problem, so it's just 3/4 divided by 1/2, so that's times 2 over 1, so that's going to be 3/2. Okay, so that proves that it's right. Okay, that didn't prove that the formula is right. I already proved the formula for you, but that verifies that it works in that case. Does that make sense? The arithmetic solid? You're going to do a lot of arithmetic with fractions in this section. Okay, let's do the same thing with this one. And just kind of work with this one. We have 1/2 plus 1/4 plus 1/8 like that. Okay, well, if you went through and got a common denominator on this, the common denominator is 8, so I'm going to change 1/2 to 4/8. I'm going to change 1/4 to 2/8. So what does that add up to? 7/8. Okay, that's the sum of that series of 3 terms. So if you use this formula up here, okay, tell me what A is in this formula. 1/2. Tell me what R is. It's also 1/2. Everybody understand that? Because 1/2 times 1/2 is 1/4, and 1/4 times 1/2 is 1/8. Okay, like that. And what's in? How many terms does this series have? 3. Okay, so let's use the formula and let's crunch it out. So we would say S of 3 equals A, which is 1/2, times 1 minus the ratio 1/2 to the third power, and then all over 1 minus the ratio 1/2. So let's work that out and let's see if we don't get 7/8 out of that. Then hopefully I've got you convinced that that formula works. Okay? All right, so let's see what we have. We have 1/2 here. We have 1 minus 1/8. If you take 1/2 to the third, that's 1/8. Okay, 1 minus 1/2 is 1/2. Like that. Now, I'm going to do something a little bit different on this one. You could go ahead and get a common denominator. Actually, I changed my mind. I'm just going to do it this way. Okay, let's just do 1/2. I'll do it the other way in a minute here. That's going to be 8/8 minus 1/8 all over 1/2. So that's 1/2 times 7/8 all over 1/2. Notice the halves cross out, so we got 7/8. Okay? So that's how that works out. All right, that's the first thing that you want to learn how to do basically in this section is if you have a geometric series, be able to find that partial sum. And what I mean by a partial sum is you're not finding the sum of the whole series, you're finding the sum of part of the series. Does that make sense? Okay, so that would be the formula for a partial sum. All right, any questions so far about anything?
So do you always look at the first 2 numbers to figure it out?
What's that?
Do you always look at the first 2 numbers to kind of...
Yeah, A is the first term. And then the ratio, sometimes the ratio is easy to see. If you can't figure out the ratio in your head, then just do this, because this will always work. Like if you take, in this series right here, if you just take the second term and divide it by the first term, that'll tell you what R is. Okay, you can pick any term and divide it by the previous, and see if you did that, you would have 1/4 times 2 over 1, so that's 1/2. Because there's going to be times when you'll easily see what R is, and sometimes you won't. So if you don't, then can't see it, then do that. Pick a term and divide by the previous one.
And that'll work pretty much always?
Yeah, as long as it's a geometric series, then it's always going to have that. If you take any term and divide it by the previous term, that's going to be R. Okay, always. Okay, that never changes. R is always a constant. Okay, so let's go ahead and work with this one then. Now what we're going to do is we're going to find the sum. This is a geometric series. So first of all, how do you know it's geometric? Well, remember a geometric series has the form like r to the k, like that, right? Or it could have the form ar to the k. Well, that has that form. It has a number to a k power. It doesn't matter what that number is. Okay, so what you need to do in this problem is let's go ahead and let's write out a few terms. You don't actually have to write out the terms on this, but just to kind of get you started, let's go ahead and do that. So if k is 0, you have a fourth to the 0 is your first term. Your second term is 1/4 to the first, and then 1/4 to the second, and so forth like that. And then you would eventually get up to 10, where k is 10, so you'd have 1/4 to the 10th power. Now, if you're finding the sum, you don't have to do that. Okay, I just want to have you do that, though. So that'd be 1 plus a fourth plus 1/16, and so forth and so forth. I'm not going to even bother working out 4 to the 10th. I don't care. Okay, so I just want to make sure that you guys understand how I write the terms out. Is that clear with everybody? Okay. Now, we're going to use the formula. So the formula is S of n is equal to A, and that's the formula I have up here at the top, times 1 minus r to the n, all over 1 minus r. Okay? So when you're finding the sum of a geometric series, that's pretty easy. Okay, so in this particular problem, tell me what A is in this series. What's the first term? 1, right? Tell me what r is. 1/4. That's what's being raised. Okay, so that is your r right there. Whatever is being raised to that power is r. Okay, so r is a fourth. Okay, now what you got to do, be careful with this. You want to tell me what n is. So how many terms are in this series? No, not 10. That's what I hear all the time. 11, right. Because you're starting with 0, okay, right? So you're going 0 to 10. If you counted on your fingers, you would do this. Now, there's a formula for this that always works too. So, I mean, it's just always 1 more. If you start at 0, it's 1 more. So you're doing like 10 minus 0 plus 1 is what you're doing. That minus that plus 1 more is how that works out. Okay, so yeah, n is going to be 11. So now what we're going to do is just plug in the formula. So A is 1. We have 1 minus the ratio, which is 1/4 to the 11th power, all over 1 minus 1/4 like that. So we need to work out that arithmetic to get that sum then, okay? And there's several ways that you can do this now, so you don't actually have to do anything with your calculator until the end. Usually I'm just going to use a calculator at the end. But to start this, what I'm going to do is, we know if we multiply this by 1, that 1 is not really important. So let's write down, we have 1 minus 1 over 4 to the 11, all over 1 minus 1/4. Okay, and the reason I'm doing that, if you don't see that, if I take a fraction and raise it to the 11th power, well, I'm doing the top to that power and the bottom to that power, correct? So 1 to anything is 1. Okay? Now what I'm going to do is I'm going to get rid of this 4 to the 11th. Okay, to me this is the best way to work with this, is get rid of the highest power. So what I'm going to do is multiply both sides, or the top and bottom of the fraction, by 4 to the 11th. Okay? And that'll be generally the simplest way to do this. So we're going to do 4 to the 11th times 1 is 4 to the 11th. If you multiply this by this, that cancels out, leaving you a minus 1. And then the bottom, you're going to end up having 4 to the 11th, like that. And then minus 4 to the 10th, like that. Okay? Now I could, let's see, go ahead and I can do it that way. Now I think I had a, no, I'm okay. what I was going to do on this is just take the calculator on this. Now I think you can also factor like a 4 out of that if you wanted to in the bottom. You could have 4 to the 11th minus 1. If you factored out a 4 to the 10th out of the bottom, you would have 4 minus 1, like that. And then that would give 4 to the 11th minus 1 over 4 to the 10th times 3. That's what I was trying to get down to, is that point right there. Okay? So first of all, what we want to make sure that we see is want to make sure you understand the arithmetic I did on there and how I know what A, R, and N is. Is everybody clear with what I mean by A, R, and N? A is the first term, R is the ratio, N's how many terms in the series. Okay? Now typically what you would do on this is just take like your calculator on this, and if you did this, I'm going to go ahead and just do on the calculator. I get like about 1.33 if you rounded it off. Now the decimals are not repeating threes on this. That's, if you actually put that on your calculator, you're going to see that that's just a rounding thing on that then. So that would be approximately what that is then. Okay? Okay, is there any questions about anything I did there? Okay? Let's go ahead and I'm going to let you run through the next one yourself a little bit, but let's go ahead and together just kind of get it set up. And with this one, this stuff right here is not too hard to do. This is not the harder part of the section. So let's go ahead and just write out some terms on this. So the first term would be 2 to the 4th. Then you'd have 2 to the 5th. Dot, 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 and eventually you'd end up with 2 to the 12th. Okay, that's what that series is if you wrote it out. Okay, now what we're going to try to do on this, we're going to try to get the answer on this one, and you can tell that it's getting bigger and bigger and bigger. The terms are getting bigger. So let's just kind of start this way. Tell me what A is in this problem. 2 to the 4th, or if you want to write that as 16, you can. Okay, tell me what R is. 2. How do you know? That's what R is right there. R is what's being raised to the power. That's that common ratio. Okay? All right? And tell me what, be careful about this, tell me what N is. How many terms are in this series? How many?
8.
Not 8. Careful. Okay? See, when you do N, you can always do this. You can go 12 minus 4 plus 1. Because 12 minus 4 is 8, but since you started at 0, or since you started at 4, there's one more term. Or you can do this, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can count, okay? I wouldn't do that, though. So it's your call, all right? So let's write down the formula now. So now what we're doing is we're doing S of 9, okay, like that. So the formula, again, that we're using is A times 1 minus R to the N over 1 minus R. Okay, now I'm going to let you guys take a couple minutes and see if you can work that out. Now you can use your calculator. I would want you to use your calculator on a problem like this because it gets pretty big. Okay, so we got N is 9, I guess is what we came up with. So go ahead and plug it in and you can use your calculator. You can also do a little bit of arithmetic simplification before you do that too, like I did on that previous problem if you want to, or you can just go straight to your calculator. And I think this one ends up being 8,000 and something. I'll have to get my calculator out and do that then. That's what I'm going to do on this, just to use my calculator. So I'm going to do like 1 minus 2 to the 9th, and that'll give negative 511, and then 1 minus 2 is negative 1. The two negatives cross out, so it looks like you're just going to do 16 times 511, And yeah, that's the sum is 8,176. So that's it. That's all there is to it. That's not a real difficult thing to do. What do you guys think? If you can figure out A, N, and R, you got it made. Okay? Then use your calculator as needed on these. Okay? All right, any questions about that? Okay, now what we're going to transition here, I want to do one more illustration of this, I think. And then we'll kind of get into the infinite geometric series and talk about the convergence and divergence on this. Okay, so this one, let's go ahead and just write everything out and get this sum right here. So we want to figure out A, R, and N. We want to use the formula S of N equals A times 1 minus R to the N over 1 minus R. So let's do one more. This one we'll just use a calculator on, okay? All right, so write the terms out if you need to. So you'd have pi to the 0 plus pi to the first all the way up to pi to the 6th. Okay, so tell me what A is. A is 1. Tell me what R is. Pi. What's N? I keep hearing a 6. 7. Okay. There's one more. Okay. 6 minus 0 plus 1. There's 7. Like that. Okay. Or count on your fingers. Take your pick. Okay. So we're going to do S of 7. That means the sum of the 7 terms. So we're going to have 1 times 1 minus pi to the 7th over 1 minus pi. Okay, and this is one you just want to do on your calculator. You don't want to do this in any other way. And then we'll just round this off to a certain number. So I'm going to do like 1 minus, I'll just do this in parentheses is the way to do it. So I'll say 1 minus pi to the 7th power. Not like that. I always do that wrong. Okay, close parentheses and then divide by, make sure you got using your parenthesis keys when you're doing this then. Okay, so that will give approximately 1409.84. I'll just round that off to a couple of decimals like that. Okay. All right, so that'll wrap us up kind of on how you find a partial sum on a geometric series. That's a pretty straightforward thing to do. Now, what we're going to talk about is an infinite geometric series next. And the infinite geometric series, you're going to represent this as k going from 0 to infinity now. And you still have that general form. Okay, you can say a to the rk. That's the general form. Of course, if a is 1, then that just becomes r to the k like that. Okay, the convergence on this is defined by what R is. And let me explain kind of what happens on this is, let's first of all look at what happens when you're out here, okay, when you're less than or equal to -1. Let me just kind of pick something and show you. Let's pick a number. Let's say that R is -2. Then I also want to show you what happens when R is equal to -1. Okay. Well, if you had something like this, if you looked at the formula, you would have k goes from 0 to infinity, and then we're just going to look at -2 to the k power like that. Okay, again, I'm just replacing r with something I'm picking. Now let's see what happens on this. Let's actually just kind of write out some terms. We'd have -2 to the 0 plus -2 to the first plus -2 to the second, and so forth. So let's see if this will help us understand whether this converges or diverges. Okay, let's see what would happen. Well, this would be 1. That would be -2. This would be 4. That would be -8. So first of all, what do you notice on the terms of that series? They alternate in sign, okay? Now notice what's happening. Of course, the terms are getting bigger too, aren't they? Okay? So that thing is going to diverge because it's alternating and it's not going to any value. And you know, if you actually plotted out the terms of this sequence, they would kind of go like this. They would just get wider and wider apart. So if you added those things together, then they're never going to end up converging to some particular value. Does that make sense? Okay, so that's going to diverge. Also, if you had r as -1, let me show you what would happen. Okay, if you did like -1 to the 0 plus -1 to the 1 plus -1 to the second and so forth, what you would end up having is you would have 1 minus 1 plus 1 like that, minus 1 and so forth like that. Now think about that one. That one's easy to think that you might think it converges. Okay, the reason it doesn't, although these things are going to cancel, well, what's going to happen? You're always going to be adding another one there. Yeah, so it's going to alternate. What you're going to have, if you did the terms of the sequence, you'd have positive ones and negative ones. And although they're going to cancel, the next term is always a 1 or negative 1. So it's not going to go anywhere. It's just going to keep alternating forever. So if you're less than or equal to -1, that geometric series is going to diverge. Does that make sense to everybody? Okay? The other thing that happens is we want to look at each situation to kind of get the idea. So let's pick something like in case 2. Something between -1 and 1. Let's say that R is 1/3, for example. Okay, let's use that. So then we'd be doing the series k equals 0 to infinity, and we'd have 1/3 to the k like that. Well, let's write out some terms and see what happens here. So we'd have like 1/3 to the 0, 1/3 to the first, 1/3 to the second, and so forth. So let's just write out enough terms to kind of get an idea here. Okay, so what you'd have is you would end up having 1 plus 1/3 plus 1/9, and if you kept going, it would be like 27, 81, and so forth like that. Okay? Now what's happening on this, as your term is getting further out, where is the infinite term going to? 1 over 81, where's that going to? That's going to 0, isn't it? Okay, so like if k is going towards infinity, then that term right there is getting closer to 0. So that one's going to converge in that idea. You're going to end up, if you just add these terms up, eventually those ending terms are going to get closer and closer to 0. So for that reason, that would be one reason we could kind of think that it would converge. Does that make sense? Okay, so that sum is going to converge to some value. Then let's take a number, let's take r equals 1, and then let's take r equals 2 and just kind of work that out. So if we were doing the series k equals 0 to infinity, and we did 1/3, nope, hold on, I'm doing the wrong thing, 1 to the k, let's kind of think about why this would diverge. This one's easy. So what you'd have is 1 to the 0 plus 1 to the first, 1 to the second, and so forth. So why would that one end up diverging? Because what is it? What are the terms? They're always 1, aren't they? So you just have 1 plus 1 plus 1 plus 1 forever and ever and ever. It's just going to get bigger and bigger and bigger and bigger without bound, right? Okay, so that's going to diverge. Does that make sense? Okay. How about if you did 2? K equals 0 to infinity. If you did 2 to the k, well, your terms would go 2 to the 0, 2 to the first, 2 to the second, and so forth like that. So you would end up having 1 plus 2 plus 4. Everybody see clearly that that diverges. Just gets bigger forever. So what's going to happen on your geometric series is if r is between -1 and 1, not including -1 and 1, you're going to converge. And we will be able to find the value of that by using a formula for that partial sum is what we're going to end up kind of doing there. Okay, does that make sense to everybody? Okay. All right, let's do a little bit more with this page and figure out if it converges or diverges. Okay, what we're interested in on this is considering whether it converges or diverges. All right, so let's see. Let's just write out a few terms. And you don't necessarily have to do this when you're doing this problem. That's not the point, but I like to kind of do this as I'm teaching this. So it's going to go kind of cycle through terms. Okay, so what is A in this problem? It's 1. Remember, A is always the first term, so that's going to be a 1. Okay, then you're going to have like 3/5. Then you're going to have, let's see, 9 over 25 and so forth like that. So that's how that series goes. Okay, what's R? 3/5. Remember, it's staring you right in the face. It's right there. That's R. Okay. All right. Now, can you tell me if this converges or diverges? Remember, it all depends on what R is. That converges. How come? It's between -1 and 1. Good. Okay, so what we'd have is, since R is between -1 and 1, we would say, therefore, this one is going to converge. We're not interested in finding out what that value is yet. We're just interested in whether it converges or diverges. Okay, that's it. Okay, all right. So let's see, the next one, if we wrote this out, okay, let's see, the first term, now this time we're starting with k equals 1. You can start the series anywhere you want to. 0 is the most common. So if we did this, we'd have -2/3 to the first, -2/3 to the second, and so forth. Okay, so just to kind of get an idea of how this series goes, let's just write out a few of the terms. So you'd have like, the first term would be -2/3. Then it looks like you would have 4/9, and then you would have -8 over 27 like that. Okay, so tell me what A is. First term. Okay, first term's -2/3. How about R? What's R? -2/3. Okay, so would this converge or diverge? It all depends on what R is. Okay, is it between -1 and 1? That's all you care about. Is that true? Yes. Okay, you have a fractional value, and it's negative. As long as it's between -1 and 1, that means that that one is going to converge. Okay, so that's the idea. Okay? Okay, again, we're not quite to the point where we're figuring out what the value of that convergence is. We just have that. Okay? All right, let's look at the next one. Now, this one is just written in, not in the sigma notation, but tell me what A is. Okay, how about R? Okay, what are you doing? Now, remember what I said, if you don't know what R is, you can always do this. Pick a term and divide it by the previous term, right? Okay, so R is 1.01. Okay, you can pick any term. Like you could take these two terms. Look what happens. You would get 1.01 to the third over 1.01 to the second. You still get 1.01. That's what R is it's a ratio of a term to the previous term. Okay, so would that converge or diverge? Diverge. How come? Because it's bigger than 1, right? Okay, so since R is greater than 1, therefore that would diverge. Okay, that's the idea. So what you want to kind of get in your mind on this is if it's between -1 and 1, it converges. Otherwise, what does it do? Diverges. That's it. Diverges means it does not, the sum ends up going to infinity or does not go to some specific value. Okay, like that. Okay? Okay. All right, let's go. I got to load up the second part of this, so let me go ahead and do that real quick here. And then we'll go through a little bit more with this. And we're going to talk about a harmonic series. And the harmonic series is a little bit different idea. So let me get this set up here. Okay, so what we're going to look at is, I need to scroll down a little further to the bottom here. Okay, so we're going to start looking at, the next thing I want to look at is what we call a telescoping series. So I want to go through a couple of examples of that, then we'll take a break. Okay, so a telescoping series ends up going kind of like this. I'm going to use this example they had in the book because this was already written out, so we don't have to worry about writing this out. So the idea with this series right here is if you let k be 1, you would have 1 over 3 to the first, and then you would have 1 over 3 to the second. So you're just doing 1 over 3 to a power minus 1 over 3 to one more power, like that. Now if you write this out, what I want you to see is kind of what happens on, this is what we call a telescoping series, is you've got 1/3 minus 1/3 of the second. Then what's happening? This goes up, the counter goes up to 2, so this is going to be 1 over 3 to the second, 1 over 3 to the third, and so forth. Does that make sense? What's happening? Okay? Now, notice what happens if you write all these terms of the series out. What do you see happening when you start adding things up? Like what happens right there? That cancels, right? And then you would have a minus 3 to the third. Well, the next term would be what? 1 over 3 to the third minus 1 over 3 to the fourth, right? So you're going to have this infinite amount of cancellation, but you're always going to end up with that first term. That doesn't cancel with anything. And then that very last term, even though that goes on forever, is still, it's not going to cancel because you're always going to end up having this cancel, and that cancel, and left over with this. So what you're going to end up with is the first term 1/3 minus that last term. And the reason I'm writing that as n plus 1, okay, that's just some general number, so I'm going out one more, okay, when I do that to find that sum. So the idea with this is going to be on the telescoping series, you're going to have cancellation there, cancellation there, cancellation there. So you're going to end up having just the first and last term like that. Okay? So that would be what the sum of the partial, and that S of n is standing for a partial sum, would just end up giving that. Okay? That's how that works out. Okay? Does that make any sense? Okay? All right? Telescoping, you want to kind of write the terms out and then see kind of how they go. Here's another example that I took out of the book. This one I did partial fractions. I'm not showing the step, but if you did partial fractions, like if you said 1 over k times k plus 1 is equal to a over k plus b over k plus 1, like you've learned, well, you would end up getting this. You would get 1 over k minus 1 over k plus 1. I'm not going through the details of that. I don't want to do that. But if we were to go through and write this out, okay, if k is 1, you'd basically have this. You would have 1 over 1, so that would be 1. Then you'd have 1 over 1 plus 1, so that would be a half. So that would be like the first term in that series. And then it follows a pattern. Now, if k goes up to 2, now you have 1/2 minus 1/3, and so forth like that. Does that make sense to everybody? Is that good? Okay. Now, what do you see happening? Canceling, right? That cancels, that cancels, that cancels. The 1/4 would cancel with the next term. And then that would cancel, okay, with the previous term. So what you would end up having is just the first and the last term like that. That's how a telescoping series works. So it does converge, and it's going to converge to this value, okay? And what we would do if we were doing an infinite series on this, then we could take the limit as n goes to infinity, and that's what we're going to end up doing. So does the structure of that telescoping series make sense to everybody? Does it make sense to you that it's going to converge? Okay, because you're going to end up with the first term and last term added together. That's what it is. Everything else is going to cancel out, okay? All right, so let me start this next one here. Get all this stuff erased on here. And we'll go through a couple of examples of how you're going to do work with telescoping series. I think I got a misprint on this B, it looks like, too, because that one is not telescoping the way it's written. Okay, so what we're going to do on this one is, first of all, it's not always obvious that it's a telescoping series. So what you want to do is you want to go through and just start writing the terms out and see if it is. Okay, so let's go ahead and start this way when we do this. Okay, so let's start with k equals 0. So we'll have e to the negative 0 minus e to the negative 0 plus 1. Usually you have to write out a couple of these and then you start beginning to see a pattern. Okay? Then if you go to k equals 1, you're going to have e to the negative 1 minus e to the negative 1 plus 1. And I'll take it out one more to k equals 2. We'll have e to the negative 2 minus e to the negative 2 plus 1, and so forth forever, like that. Okay? So let's kind of write this out a little bit better now. Of course, that's going to be 1. E to the 0 is 1. Then this is going to be minus e to the negative 1. So that's going to be what you get in that first parenthesis. Second parenthesis, you're going to have e to the negative 1 minus e to the negative 2. Third parenthesis, you're going to have e to the negative 2 minus e to the negative 3. So does that look telescoping to you? Okay, you guys see what I mean by that? Okay, got a bunch of cancellation. Now, if you went through and if you wrote this out a little bit further here, you would eventually kind of get out like this. Okay, if you go all the way out to the end and just write down what you have there, eventually you would get out to e to the negative k minus e to the negative k plus 1, like that. Okay, so that's how you would want to write out the terms. You want to write out enough terms so that you see it's telescoping. All right, is everybody clear with how that's written out? Okay. All right, now let's cancel some stuff. That cancels, that cancels, that cancels. You would have an e to the negative 3 in the next term, and then you would eventually make it up to e to the negative k, which would cancel that. So what you're left with is the first term, and you're left with this very last term here. So what you're going to be left with is 1 minus e to the negative k plus 1. Now, if we're going to find the value of that, what we're going to do is we're just going to now do the limit as k goes to infinity, because we are doing an infinite series here, of 1 minus e to the negative k plus 1, okay, like that. Okay, so if we can do that limit, then we got it made. All right, so I'm going to do this way. I'm going to write this. You can always take a limit of a difference and break it up into two limits. You can also do this in your head. You could reason this out in your head. So it's the limit as k goes to infinity of 1 minus the limit as k goes to infinity. And see, what I'm going to do is I'm going to write that negative exponent as positive. So I'm going to write that as 1 over e to the positive k plus 1, and that limit's going to infinity, like that. Okay? All right, well, let's finish it up. So what's the limit of 1? 1. Limit of a constant's constant. What do you think the limit of 1 over e to the k plus 1 is as k goes to infinity? Where's that going? 0, exactly. Because, see, this thing is really 1 over an infinitely big number, right? That's e to the infinity plus 1. So for all practical purposes, that's 1 over infinity, so that goes to 0. So that means that the sum of that infinite series is 1. Okay, if you actually wrote those terms out, I mean, think about this. If you wrote out the first 3 terms, it's obvious, okay? The first 3 terms, the partial sum's 1, isn't it? Right? Okay, and then if you want another term, you would always have all that cancellation, but you'd end up with a 1 right there. Does that make sense? Okay, so that's how that telescoping series is going to work that. Let's look at one more of these, and then we'll take a break. So I want to finish up this problem here, then we'll break. Okay, so this one was a typo. This is not telescoping the way it is. So what I think I did when I typed this off, I think this one had to have been intended to be a 2, or either the other one was k plus 2. Okay, those things are 1 apart. So I'm just going to change that to k plus 2 like that. Okay, well, let's go ahead, let's write out the terms. And you can do most of this in your head. So if k is 1, you would have 1 over 1 plus 2, or you'd have a third. If k is 1 there, that would be minus 1/4. Just do that in your head. Okay, the next term, now we're going to k equals 2. So you'd have 2 plus 2, or 1/4. then you'd have minus 1/5. And we'll write one more out. Then it would go to 1/5 minus 1/6. And then let's go ahead and just write down whatever we're doing. So let's write that as 1 over k plus 2 minus 1 over k plus 3 like that. Okay? All right, is that everybody clear with how that's written out? Okay, does that look telescoping? Yeah, because you got that cancellation, right? So the thing is, there's your cancellation. That cancels, that'll cancel, and that'll cancel, actually. You'll always end up with that last term there. So if you can kind of see if you did the first 3 terms, what if you just did the first 3 terms? Then what would be the answer? 1/3, right? Well, it doesn't matter. If we went to infinite terms, wouldn't you still end up just having 1/3? Okay. Now I'm going to do that a little bit more analytically to prove that to you. So what we're going to do now is we're going to do the limit as k goes to infinity of what are we left with? We're left with 1/3. That first term didn't cancel, so we got that. And then that last term didn't cancel. So we got 1/3 minus 1 over k plus 3. Then we're going to do that limit as k goes to infinity like that. Okay? All right, now you can do this in your head. I mean, you could just write the answer if you want to. But specifically, you're doing the limit of k goes to infinity of 1/3 minus the limit as k goes to infinity of 1 over k plus 3. Okay? So the limit of 1/3 is 1/3. And tell me what the limit of 1 over k plus 3 is. 0. How come? Because that's 1 over infinity, right? Which we see over and over and over again. So that's like 1 over infinity, so that's going to 0. So we'd have 1/3, like that. So you see on the telescoping series, you're pretty well getting that first term, aren't you? Okay, that's the way it works out, and that's how you would verify and do that on a telescoping series. Okay, so how does that look to everybody? Okay, is this interesting? It is kind of. It really is, okay? The idea that you can add up an infinite number of numbers and it can have a finite value is kind of interesting. It's been something that people have been kind of puzzled over, even for over 1,000 years, actually. People were investigating this stuff before calculus even existed. All right, let's go ahead and let's break here then. Continue with this then. All right, so what we're going to do now is we're going to look at some infinite series. So this one we're going from 3 to infinity. Generally, you can start k anywhere you want to, but this is an infinite series. And we want to see if it's geometric. And a couple of things that I want to mention is we've already learned that if you have like a geometric series that's not infinite, if it's just going from whatever, it can start anywhere and just goes to n, then we learned, and we were working with this, that you can use that formula to find what we call the partial sum. Okay, if you have an infinite series, a geometric series, then as we learned that as long as r was between -1 and 1, then it's going to converge. But I didn't show this, and I'm just going to give you this formula, is that if it does converge, then that's going to be the formula is a over 1 minus r, okay? And that I'm not going to derive or prove that, but that comes from the idea of taking the limit of this partial sum formula as n goes to infinity. And that's a fairly challenging thing to do. R has to be between -1 and 1, or it's going to diverge like we learned. So what we're going to do is, if we figure out that it converges, then we're going to find the value by using that formula right there. So we can find the value of the convergence on a geometric series using that formula, okay? So I'm going to show you 2 ways to do this. Most of the time, you're just going to use the formula. You're going to figure it. You want to rearrange this and make sure that you see that this is a geometric series. So the first thing I'm going to do is let's write this, kind of rearrange this and write this as 3 to infinity of 3 times 4 over 7 to the k. You can do that. Does that make sense to everybody? Okay, if you have like a number to a power and another number in the denominator of the power, then that whole thing is to 1 power. Agree? So that's 4/7 to the k. Now, is this geometric? Does this look geometric to you? what's the structure of geometric? A, R to the K. So we do have that. See, we have A being that, and then we have R being that. Now, can you tell me if that converges or not? All depends on R. R is 4/7. Does that converge or diverge? It converges. How come? Because it's between -1 and 1. So you got to make sure, okay, I got a geometric series. I know it converges. So that means I could go directly and plug this formula in to find the value of that infinite series like that. Okay, so I'm going to show you two ways to do this. Most of the time, like I say, you're going to do the second way, but I'm going to go ahead and do it like this. So I'm going to write this as the series from k = 3 to infinity. And then what I'm going to do is, since this thing is starting at 3, I'm going to go ahead and write this as 4/7 to the third, like that. And then I'm going to write this as 4/7 to the k - 3. I'm just showing you two ways to do this. I think most of the time you're going to probably prefer to just do it the second way. Now, does everybody understand that I have not changed the problem? Let's make sure we understand that, okay? So if you added those exponents, what would you get? You get k, all right? The reason I started that with a 3 is because the series started at 3. If that was a 4, I'd do a 4 and a k - 4 like that. So this is one method to do. If you want to do this method, you can do it this way. And what will happen on this then is you'll have this then. This right here, that's a constant, right? Well, what can you do with a constant? Like on an integral, you take it out. You do the same thing with a series. A series is like an integral, okay? So what you can do on that is you can take that constant out. So we'll have 3 times 4/7 to the third multiplied by the series from k = 3 to infinity of 4/7 k - 3 like that then. Okay, so then that's what we'll have. And then what we can go ahead and do, if you worked all this out like on a calculator, if you did this right here, that would be 3 times, let's see, 4 to the third I think is 64. 7 to the third is 343. So you could do that, okay? Then what we would end up with is just the series k = 3 to infinity of 4/7 to the k - 3 like that then, okay? Then what we can do is this, I think, if you put that over 1 and multiply, I think that's 192 over 343. And then you can apply this formula now. So you can end up using this formula right here. So if you use this formula, then it's going to go like this. Okay, first of all, if you look at this series right here, in your head, can you tell me what A is? Right here. Because you start with k = 3, so what are you going to have? 4/7 to the 0, right? Everybody see that okay? 3 - 3 is 0. If you start with 3, you would have 4/7 to the 0 is 1. So I'm going to take this formula right here. A is going to be 1, and then the ratio is this thing, 4/7. So what you would have is you would have 1 minus 4/7. Okay, see, this is, once you establish that you have a convergent geometric series, this is the formula that's going to give you that sum, A over 1 minus R. Okay, so then if I did this, now the way I'm going to go ahead and do this is I've got that constant, and then I'm going to get rid of that 7. So what I'm going to do is I'm going to multiply the top and bottom by 7 here. So I'm going to multiply that by 7. Multiply that by 7, and that's just going to get rid of that fraction for me. So I'll have 192 over 343, and then 7 times 1 is going to be 7, and then down at the bottom, 7 times 1 is 7 there, and then when you do this times this, the 7s are going to cross out, leaving a 4, so you're going to have 192 over 343 times 7 over 3 like that, okay? Then you can go through and just multiply out the fractions, and then you'll have what that value is. Okay, so now what you can do here is I think you can reduce this. So I think 7 goes into 7 once, 343 divided by 7, I think, is 49. Okay, and then 192, 3 goes into 3 once, 3 goes into 192 64 times, so you get the answer, you have 64 over 49. That would be the value of that infinite series, believe it or not. Okay, so if you take this series right here, that would be the value of adding up that infinite number of terms. Isn't that weird? Okay, but to me that's just weird. And you can take an infinite number of numbers and add them up to a finite number. Okay, that's it. Okay, now that's one way to do it. You might prefer doing it the second way and just always crunching it out. So one thing that you could do is just leave this alone. So if you start with just this sequence right here, now I'm going to look at it like this. You definitely want to write it that way first. So let's just write down that you've got the series k equals 3 to infinity of 3 times 4/7 to the k, like that. Okay, now we're going to use the formula a over 1 minus r. We do know this thing converges because the ratio 4/7 is between -1 and 1. Okay, well, all you got to do is figure out what a is, the first term. Okay, so you can just do this. The first term would be 3 times 4/7 to the 3rd power. Now, I want you to notice on this, okay, the reason I'm teaching you 2 ways, you can take your call on this. See, when we did it right here, this thing right here is this. That's that constant we pulled out of there anyway. So you could go ahead and get this. This would be 3 times 64 over 343, and that would be what the value of a is. And then r is going to be 4/7, right? So remember, a is just your first term in that formula. So let's go ahead and crunch that out then. So this is going to be 3 over 1 times 64 over 343. And let's see, 3 times 64, I think, is 192 over 343. Okay, so that's what a is. And then r is going to end up being 4/7. Okay, so we got everything that we need to know. Now we're going to apply this formula a over 1 minus r. Okay, so let's plug in a as 192 over 343, and then 1 minus 4/7. Like I say, I think most of the time you guys are going to prefer to do it that way. Okay, it's just less steps. You end up having the same idea. So what I'm going to do with this one then is, again, because I have a complex fraction, if I want the 7 to go away, I need to multiply the whole denominator by 7, and that forces me to do the top by 7 like that. Okay, when I do that, it goes like this. Let's see, 7 goes into 7 once. 7 divides into 343 49 times. Okay, go to the bottom, you'll have 7 times 1 is 7, and then you'll have that cancellation right there. Okay, so what you'll have is you'll have 192 over 49 in the numerator. Then the denominator, you have 7 times 1 is 7, minus 4. So that's 192 over 49 all over 3, like that. Now that's a division problem, so you can write this as 192 over 49 divided by 3. So you can do the reciprocal, so you have 192 over 49 times 1/3, and then that reduces down to 64 over 49. So there's a lot of arithmetic in this. It's not hard arithmetic. You generally have complex fractions popping up, so the way I always do this is just multiply to get rid of them. You could also do this if you wanted to. You know, it's kind of your call with whatever you prefer to do. If you were doing this problem, you could also say this is 192 over 343, and then this is 3/7. Okay, if you did like 7 over 7 minus 4/7, you would get that, and then you could just do that division problem. It's your call. Okay, but I think you'll do okay with that. Once you determine that it's a convergent geometric sequence, A is the first term, R is that ratio. Crunch it out. There's nothing to it. All right, is everybody clear with that? Okay. All right, let's move on. Let's do one additional one here. Now, I'm just going to start doing these the second way over and over again. So, first of all, what you want to do on this is this does not have the form of a geometric series yet, because that's got to be a k power. Remember, the general form is series, k goes, starts somewhere, goes to infinity, and you're looking for AR to the k, not negative k. It's got to be k. So you got to make sure you put this in the form. So let's work with this a little bit before we do this. So we could write this as the series k goes to infinity. And what you could do is, you can do this all in your head if you want to. I'm going to just kind of carefully show steps so we know that, right? Well, what can you do with negative exponents? You can make them positive, right? You could flip these. You could move this to the bottom, and you could move that to the top. So what you would have is the series 0 to infinity of 3 to the k over 4 to the k, like that. Okay, now I'm going to write this one more step, and then that will give us how we want to rearrange this. So you can write that now as 3/4 to the k power. Now you could do that all in your head if you're comfortable with doing that. I don't care. Okay, now is that a geometric series? Absolutely. It's something to a power, right? Does that converge? Yes. How do you know? That ratio is 3/4, and that's between what two numbers? I got 1 and 1. So it does converge. So that means we can now figure out our answer. So we just need to know what A is, and we need to know what R is. Then we need to apply the formula A over 1 minus R to get that sum. Okay? All right, well, A you can do in your head. If K is 0, then you have what? 3/4 to the 0. So that means A is 1. Okay? R is 3/4. Okay, so we got that. All right, just plug them in then. So this sum, you're going to have 1 over 1 minus 3/4. Okay, like that. Okay, and then I'm going to just multiply the top and bottom by 4. That's the way you'll see me doing this most of the time, is like this. So I'm going to have 4 in the numerator. The denominator is 4 times 1 is 4. Multiply that out, you get that, and that's 4. That's pretty cool. So that crazy series, 4/3 to the negative k, will add up to 4. Okay, if you do that infinite series. Okay, not the partial series, but the infinite series will converge and it'll have a sum of 4. Okay? All right, does everybody see what I'm doing on that okay? So see, a lot of what we're doing here is if you figure out A and R and you know the convergence, then it's arithmetic to figure that out. Everybody see that okay? All right? Okay? Okay, let's continue on with a couple of more of these, and then to finish up this section, we're going to, I've kind of taught you everything I need to show you. Just want to do some different examples. Okay, sometimes when you're working with a series, I might not give you the sigma notation, but I can write it this way. So what you want to do on this is you still want to figure out what A and what R are, and figure out, is this a geometric series? Okay. Well, what's R in this, or I'm sorry, what's A in this problem? Okay, 1 over 16, without a doubt. That's the first term. Now, if you don't know what R is, well, what I said you can always do is pick a term and divide it by the previous term. Okay, that'll always give you what R is. And you probably need to verify that, you know, once you figure out what R is, make sure that this is a geometric series before you go on and apply your formula. So that's going to be 3 over 64 times 16 over 1. Okay, that will cross out to 1/4. So that means that we have R is 3/4 and we have A is 1/16. Well, let's make sure this works. The idea would be, if you do 1/16 times 3/4, notice that you get the second term 3 over 64, right? Then if you did 3 over 64 times 3/4, that's going to give 9 over 256. So it appears to be working. Okay, so are you convinced this is a geometric series? Okay, that's the idea. So now we know that if R is 4, does this converge or diverge? Converges, because R is between -1 and 1, right? Everybody got that? So now we're ready to find this sum. So we're going to use the formula A over 1 minus R. Okay, A is the first term. That was given as 1 over 16. R is 3/4. Okay, so we have that. Now, if you want to get rid of the fractions by multiplying by 16, you can. You may prefer to do it this way. I'm going to vary this to kind of give you your two choices. You could get a common denominator and do it this way if you want to. So that would be 1/16 over 1/4. Okay, so what you're really doing is you're doing 1/16 divided by 1/4. So that's 1/16 times 4 over 1, and then that will reduce down to 1/4. So the value of that infinite geometric series, it sums to 1/4. Who would have thought? But it does. Okay? Crazy, isn't it? Okay, I think it is. Very interesting that this works out the way it does. Okay, any questions on that? Okay, all right. So let's see what we got on the next one here. Now, first of all, is this thing written in a form that's a geometric series yet? No, because it has to say something to the k power, right? So well, you want to play with this a little bit. And watch carefully how I do this. This is one of the key things you got to learn how to do. This is kind of a geometric series in disguise. So the first thing I'm going to do is, since I have a negative exponent, what's something you could do? You can make it into a positive exponent, right? Okay, you can do that. Now remember, your goal is to have something to the k power. Well, you can do that. And the idea behind this is you could think of it this way. You could think of that 1 to the k because 1 to any power is 1, right? So I'm going to write that as 1 to the k. Then I'm going to write that as negative e to the k like that. Okay? So that means I could rewrite this as the series from k equals 1 to infinity of 1 over negative e to the k. Now, is that in the form that we would expect a geometric series to look? Absolutely. That form is a r to the k, or even just a to the, r to the k if a is 1. All right, so we've got that written now as a geometric series. You know you've been given that. The next step is to figure out if it converges or not. So what do you want to know about that 1 over negative e? If it converges, where does it have to fall? Negative 1 and 1. Okay, so you have to know that. So let's make sure that that's true. Okay, negative 1, you could write that as negative 1 over e less than 1. That is true, isn't it? Okay, it's definitely true. Okay, because that's just some fractional value. E is 2.7. So this is a kind of like, it's a fraction that's pretty close to negative 1/3, right? So that means that this is going to converge. So then we can go ahead and we can just use our formula. Okay, so that sum is going to be given by the formula a over 1 minus r. Okay, like that. So a is going to be the first term. So we need to go ahead and figure out what that is. So notice that k is 1. So you're going to have 1 over negative e to the first power. And that's a negative number, so that's negative 1 over e. Okay, so we have a is equal to negative 1 over e. Okay, now can you tell me what r is? 1 over negative e, same thing. Okay, that's r right there. That's what's being raised to that power. So that's going to be exactly the same thing. All right, everybody good so far? Okay. Let's crunch it out and see what we get. So a is negative 1 over e. Then we have 1 minus negative 1 over e. So you want to be kind of careful about how you handle that. So then that would be negative 1 over e. And then this would be 1 plus 1 over e like that. Okay, now what you want to do is you have a complex fraction. What would you want to multiply by so that it's not complex anymore? By e. Okay, get rid of the e, make it go away. So multiply the top by e, and then multiply the bottom by e like that. Okay, that's going to cross that out. So you'll have negative 1 in the numerator, then e times 1 is e, and then if you multiply those terms, that's going to cancel out. So that would be the exact value of that infinite series. That's what it sums to. That's the value. Okay. Most of the time, you know, we're only going to look at certain series that we get a value to. Most of them we're just going to determine if they converge or diverge. But a geometric series is easy to figure out that value once you know it converges. Got to know A and R and then do arithmetic. That's it. Okay? All right, any questions? Okay. All right, now once we get past, I generally find like the first 3 sections don't go too rough for students. It's kind of when you start getting into the different types of tests that we're going to do, learn all these different types of convergence tests, that's when it gets a little bit more complicated for students. All right, so let's do one more of these, and then we are going to start lightly in 8.4, where we start looking at the divergence test and the integral test. We're going to look a little bit at that today. Okay, this is partial fractions. Now, first of all, how do I know that partial fractions would be useful? If you were doing an integral, doesn't that look like partial fractions? Why does it look like partial fractions? It's my question. Well, you got something factored in the bottom, right? Okay, that's kind of what you're used to seeing, so that's going to be partial fractions. So at this particular stage, it's hard to tell what we have. It doesn't look like geometric, that's for sure. Okay, so let's go ahead and let's write kind of the setup for partial fractions. We're going to do 1 over 3k plus 1, 3k plus 4, that's already factored. And we're going to say these are simple linear factors, so what do? You say a over the first, then you say plus b over the second like this. Now this one could possibly be telescoping. Maybe it's geometric in disguise. That's what we're going to find out here. So we're going to have to start playing with it to kind of see what we have. All right, so let's go ahead and multiply everything by 3k plus 1, 3k plus 4. And then we'll get our system kind of set up. And then we'll see where this leads us then. Okay. All right, so let's see what we got. Now that's going to cancel out, of course, leaving you 1. Over here, that's going to cancel out. Now I'm going to go ahead and just multiply this out. So that's going to be like a times 3k. And then that's going to be a times 4 is going to be plus 4a. It just kind of gets the a's together like this. Over here, this is going to cancel out. So that's going to give b times 3k and then b times 1 like this. So you got to get your system and find a and b is the key that we've done. Okay. So let's say when we put this together, let's put everything that has a k together. Let's get these two things together. And then let's get these two things together because we're equating the powers of k is what we're doing. Okay, so this is going to give me, when I put the stuff in yellow together, I'm going to have 3k, when you factor that out, times a plus b, and then that'll leave me with 4a plus b like that. All right, does that look familiar to everyone? Okay. Now let's see if we know this now. Okay, can you tell me what a plus b would have to be equal to? You even have the 3 there also. Is there a power of k out here? Now, there's not like a k to the first or something like that. Technically, you could think of there as being a 0k to the first, right? So that means that you would have 3 times a plus b being equal to 0. Okay? Now, can you tell me what 4a plus b would have to be? That's the constant term, so what's that equal to? It's equal to 1, right? Okay, so what we're going to have then is we're going to have 4a plus b is going to be equal to 1. Okay, now we need to solve that system. One thing that you could do on this is you could divide this by 3 so you get a little bit simpler system. So you would have a plus b is equal to 0 and you have 4a plus b is equal to 1. So you can solve that system with the different methods you've learned how to do. I'd probably just do elimination on this. So what I'm going to do is I'm going to multiply that by -1. You can do this in your head if you want to. So that's going to be -a minus b equals 0. And then 4a plus b equals 1. It's going to cross that out. That's going to give 3a equals 1. Divide by 3, you're going to get A equals 1/3. Okay, like that. Okay? And then going back to this equation, A plus B equals 0, well, B is going to have to be negative 1/3 like that. Okay, so that's the system. Is there any questions about anything I did there? Okay, we have a lot of experience in doing that. And, you know, when you get to your gateway test, there's always one partial fractions on there. So you want to know how to do that. Now, we're working with a series, but it's the same idea when you're working with an integral or a series. Okay, so if we go back to the beginning, okay, here's what we're looking at. We're looking at this and we're looking at this. So what I'm going to do is I'm going to change this series to this format, and we're going to kind of see what we have. So we have a series k equals 0 to infinity. Now we're going to have a over 3k plus 1. Okay, so if we do this, a was 1/3, so we have that. And then we have plus b. Well, let's see, b was minus 1/3 over 3k plus 4, like that then. Okay, so this thing doesn't look geometric. What it could be is it could possibly be telescoping. Let's write out a few terms and let's see what we get on this then. So one thing that you have on here is you could factor a 1/3 out of here too. So I'm going to do that now. I'm going to take that 1/3 out of the series. And tell me if you understand what I'm doing here, because I'm doing this in my head. That would leave 1 over 3k plus 1, and then minus 1 over 3k plus 4 like that. That's a constant. You can take advantage of that. You can take a constant that's multiplied by something out of the series. Okay? So I've taken that just kind of out of the top like that. If you distributed it through the numerator, you get the same thing anyway. So what do you guys think? That might be telescoping. It certainly doesn't look geometric. It doesn't have the AR to the K structure to it. So let's write out a few terms and let's see what we have. So we have 1/3, and let's just start with K equals 0. Okay, so if K is equal to 0, we would have 1 over 1 there. Okay, and then this would be 1 over 4, like that. Okay, so we have that. Now go to K equals 1. Okay, so if we go K equals 1, you can do this in your head. That would be 3 plus 1, that would be 1/4. Okay, minus, and then if K is 1 there, that looks like 1/7. Does that look telescoping already? Yeah. Okay, that's my sneaking suspicion, is that this is telescoping. I'm going to go out one more just to make sure. Okay, so let's go to K is 2. That would be 3 times 2 plus 1 would be 1/7. And then 2 times 3 would be 6, plus 4 is 10. So now we kind of got the structure. Then I'm going to go all the way out to the end where I have 1 over 3k plus 1 minus 1 over 3k plus 4 like that. Okay, so that's the idea. All right, telescoping. All right, is everybody with me okay on this one? Okay, all right, and partial fractions, when you have that structure, telescoping often is what it ends up being. Okay, so what's going to happen is that's going to cancel, that's going to cancel, that's going to cancel. Like we learned, everything is in fact going to cancel except that and that. And we are doing an infinite series, so we're going to have to do a limit. So what we're left with is 1/3 times 1 minus 1 over 3k plus 4, like that. All right, so that would be just basically a formula for that infinite series. So what we're going to do now is we're going to do the limit as k goes to infinity of this whole thing right here. Now see, that 1/3 is a constant, so it can come out of the limit. Then you would have 1 minus 1 over 3k plus 4. Can you tell me what the answer to that whole problem is? 1/3, exactly. Because what's going to happen is, and you don't have to write all this out, you can do this in your head, but you're really doing the limit of 1, and then you're doing the limit of 1 over 3k plus 4. Okay, well, that limit's 1, but what's 1 over 3k plus 4? That's really 1 over infinity, so what's that? 0. So you have 1 minus 0 times 1/3, So that's going to give you a value of 1/3 like that then. That's how that goes. And see, telescoping, once you see it's telescoping, you end up just having the first and last term left over, but you had that constant from earlier in the problem. That's the reason it ended up being 1/3. So that's kind of a different, that's not geometric. That one turned out to be telescoping, and sometimes they can be that way. That's a long problem with a lot of work. It's not difficult because it's basically applying everything that we've learned. Okay? Is there any questions you guys got to have on that? Okay, I see some blank faces out there. I know it's Monday morning, but okay, that's the idea. All right, so that'll wrap that up, and let me go ahead and close this off.